Well, good morning, students.
Sir, good morning, sir.
So, in previous classes, we have seen a couple of things like basis of a vector, independent vectors, rank, row times column, column times row, their meanings, and a couple of more things. Row
Excuse me, sir.
space, column
Sir, can
space.
you please start the recording?
Yes, yes, yes. Thank you. So, there are so many things that we have seen in the previous classes, and but that is not the end. There are so many more things that we need to talk about. One of them is orthogonality. One of them is orthogonality. This particular orthogonal creature comes quite often in linear algebra. Orthogonal, something known as perpendicular. Yeah, and we have already talked about basis. So, basis is a set of independent vectors that spans a space. Now, having said these two, basis and orthogonal, perpendicular, we have already been talking about one of the basis vector quite often, that is known as your the standard basis. This is I cap, this is j cap, and this is k cap in 3 dimension. The standard basis vectors, and these basis vectors are again orthogonal to each other, isn't it? And another important properties of this is this I cap, j cap, k cap are of uh, are unit vectors, or so to say, they are orthonormal. Now, for all these orthonormal, yeah, in orthonormal, this is also perpendicular, but then the it is of unit length. Okay. Now let us start with this one, like Pythagoras theorem. Let us go back to Pythagoras theorem, your school days. Mm, P Y T H. Okay, so let us talk about 2 dimension first, right? So let us have a vector. mm, Let us have a vector 2 0. Let us have another vector 3 0. Okay, or let me draw it here itself 3 comma 0. This is not 3 comma 0 actually. This is 3 comma 0. So the resultant vector would be this. So what is the resultant vector?
2 comma 3.
2 comma 3. So the length here, the vector length is 2, the vector length is 3. And what is this length? 2 square plus 3 square is equal to 13 square. That is the length of the vector 13. No, I mean the square of the length of the vector. So the length is actually 13. Sorry about that. This is how we actually denote it. Um, how we denote it? We denote it in this way. Length is equal to the second norm. We talk it about, it is the norm symbol, and we give here 2. That is the second norm. If we do not give 2 also, by default it is called as a second norm. And the square of the second norm is equal to, let us say this is x1, y1. So this becomes x1 square plus y1 square. Okay. Now the same thing can be extended to 3 dimension also. X1 square plus x2 square plus x3 square, or x1 square plus y1 square plus z1 square, and like that. So what is the meaning of all this? Meaning of all this? We have been seeing this base square plus height square, square root of base square plus height square. That is what is the Pythagoras theorems is all about. From here all the sine theta, cos theta, everything came. Now let us extend this one. This is in 2 dimensions. This we have been studying from the school level. If we extend this one to 3 dimension, this becomes let me put it as, because it is x, let me put it here. It would be just for the sake of notation, x2 let me put. So up to for n dimension also it is the same thing.
Hello.
Yes.
Sir, if we are putting square on the norm, then we don't put square root on the right hand side.
Oh, ठीक. Chalo. Sorry about that. Mhm. Correct. Okay. So basically, it's a vector. X is a vector 2 comma 3 here in this case, or in 3 dimension case it is x1, x2, x3. In n dimension case it is x1, x2 up to xn. Now, how we are calculating the length? That is square root of sum of all the squares. Okay. Can I write it in this way? X transpose X. Yeah. So this X transpose X is the length, uh, squared length. Squared length. Or here if you see, this becomes 2, 3, 2, 3. That is equal to 13. Okay. Okay. Let me have two vectors X and Y. Two vectors X and Y. Um, how do I know that these two vectors are perpendicular or not? You can say directly the formula is X transpose Y is equal to 0. But then how do we reach that? The simple concept. Sides of the right angle. What this X is actually? X is nothing but x1 square plus x2 square xn square plus y1 square y2 square yn square is equal to x1 minus y1 square plus x2 minus y2 square xn minus yn square. Can I write this right hand side like this? Let me expand all this a minus b whole square in that form. So this becomes x1 plus xn square, that is a square, plus b square y1 square plus yn square minus 2 times x1 y1 xn yn. Left hand side and right hand side, if you see, this is the extra terms that we have. This is the only extra term that we have. This is the only extra term that we have. And that is what we call it as, I've already told you about the inner product or dot product. Simply we say x dot y, yeah, or we say x transpose y. If this x transpose y is equal to 0, then x, y are orthogonal. Now, if they are equal to 0, is there any possibility that this will be less than also 0? What is the implication of this? The then x and y are orthogonal or they are perpendicular? Yeah, x perpendicular y, 90 degree. Otherwise, they form an obtuse angle and acute angle. Acute means less than 90, right? Yeah. Can you tell me one vector? Tell me a vector which is always perpendicular to all the vectors. Tell me one vector which is always perpendicular, which is perpendicular to itself, which is perpendicular to every vector that is possible in Rn. That is the zero vector. Zero vector is the only vector which is perpendicular to itself. Further, it is perpendicular to um, all vectors in Rn. Okay. Few more things that we must know as when do we call the vectors are linearly independent? Vectors are linearly independent when they are mutually orthogonal. That is, you take any vector that is perpendicular to every other vector. Okay. If you recall the very first class, we started with Ax equal to 0. Then we talked about column space, row space, column and row spaces. These are the things we talked about. Let me introduce one more space, which is also known as null space. What is a null space? Column space. This is the matrix A. We talk about the space that is spanned by the independent columns of this matrix A. Similarly, independent rows of matrix A. Now let us just analyze this. A times X here, and let us say this is equal to 0. 0 means what? This is 0, right? And this is first value, second value, this is nth value. So that means this row 1, row 2, row n or as many number of rows you have, that doesn't matter here. Like the number of elements in row 1 has to be n. So this row 1 times x1 is equal to 0. Or in other words, the row space of A times the solution of Ax equal to 0 gives you 0. That is how, if we can interpret. That means this row 1, if I call this one as one vector, so this vector, I'm sorry, this is not x1, huh? This is x. This complete is x. Row 1 times x. Let me put here dot. Row 1 times x. rho 1 times x equal to 0. So this vector rho 1 vector and x vector, they are also perpendicular, right? Inner product. So we have one null space. The null space is nothing but the solution space of the equation Ax equal to 0. It is the space um, that contains solution X. This contains null space contains solution X to the equation Ax equal to 0. And the row space is orthogonal to null space. So the point of saying is it is not only the vectors which are orthogonal, it is the span of those independent vectors are can also be orthogonal. Or in a mathematical term, if I write, this is column space of A transpose is perpendicular to null space of A. Yeah, one more thing about this orthogonal. This orthogonal uh, has a they have been they are being utilized quite a lot. And okay, let us talk about this. Have you come across this matrix? Uh, have you ever come across this matrix? Have you ever come across this matrix? What is this matrix is called about? Look at each column of this matrix. What is their property? What is the property of this? Each column, let us forget about the matrix, talk about each column.
Sir, they are symmetric.
Yeah?
They are symmetric.
I couldn't get it. There is?
Sir, skew symmetric, sir.
Skew matrix. No, I couldn't get it.
Sir, he says skew symmetric matrix.
Skew symmetric matrix. What did you say?
Yes, sir.
Okay. Okay. Let us say this cos theta, sin theta, transpose cos theta, sin theta. How much this is?
So 1.
I have written only the previous equation, huh? X transpose Y, and here I have written something. Acha, normal I have not written. Yeah, squared length, X transpose X, and all those. Yeah. So cos theta, sin theta, this is your X transpose X. This is equal to 1. So X transpose X equal to 1. That means this is an orthonormal vector. So each column is an orthonormal vector, right? It's an orthonormal vector. And this matrix is very famously known as a rotation matrix. Rotation. If at all you have studied in graphics, computer graphics, this rotation matrix you must have studied. So this is, yeah, and what is your, how do I represent that? What is, let us find out. Q transpose Q. So let me call it as Q. Q transpose Q. How much that is? Cos theta minus sin theta, sin theta, cos theta, cos theta minus sin theta, sin theta, cos theta. So that is equal to 1, and this one is cos theta minus sin theta, cos theta. This is 0, 0, 1. Or so to say, this is equal to identity matrix. So two orthogonal matrices. Orthogonal matrix, I mean, sorry, not two orthogonal matrix. A matrix is orthogonal. This condition square matrix is orthogonal, this condition holds. Now, there is one important property with this orthogonal thing is, whenever you use this orthogonal matrix to any vector, they do not change the length, they only rotate it. They do not change the length. Say for example, we have this vector and so let us talk about any vector. So let me put a vector at 30 degree. What happened? Hello, can you hear me?
Yes, sir.
Sir.
Then this mic is working. This is something problem. Oof. This one got stuck. This whiteboard. Yeah. So this is theta. So whenever we talk about a point, let us say okay, let me call this one as 1 comma 0. So what will be the coordinate of this? The length of this vector is 1. So this vector length is also 1. And yeah, this vector length is also 1. And this value, this value would be cos theta minus sin theta, cos theta, 1 0. Yeah. and this is nothing but uh, this is nothing but reflection of a point 1 0 this is 15. Now this is about a point. This is all about a point 1 comma 0, and this is something like a reflection about a line which passes at through origin at an angle theta by 2, and this 1 comma 0 when rotated by an angle theta makes this particular point. And similarly you can find out about this any any other point. So it actually rotates the entire plane by an angle theta, and this is one of the very beautiful example of orthogonal matrices. Well, uh, there are a lot many things are there. We'll talk about it in the next class. That's all for today.